So we've been looking at the situation of the vibrating string from the point of view of an initial and boundary value problem, in which we have a string which is bound at both of its ends. So its shape at an instant in time is described by a function y of x and t. It's displacement from equilibrium, with both ends fixed so that y of 0 comma t, y of L comma t, and y of 0 comma t both being 0. And its physical considerations telling us that it will vibrate according to the partial differential equation, ytt equals a squared times yxx, where a is a constant relating to the tension and material of the string. And the new thing that we started doing a week ago was giving this function an initial distribution, an initial shape at time 0. So in this particular animation, I'm giving it an initial shape that looks like this sawtooth point. So I take the guitar string and I pull it up to a point in the middle and imagine that it's just a straight shape. I'm going down from that point down to both ends. And that's what we call the initial distribution, the initial condition, the initial profile, whatever you want to call it. And it corresponds to f of x comma 0 is a graph that might look like that. We've been using a horizontal line at 1 to motivate our initial discussion. For this particular animation, it's this little point function, this tent function. The idea being that we know that solutions of this boundary value problem are going to take the form y of x and t equals some gigantic sum of some constants that we need to talk about today, times times a time dependence that looks like cosine of n pi a over L times t, times a space dependence that in this example looks like sines of n pi over L times x. And that we'd like for this summation to include as many of these terms as it takes to exactly match our initial shape. Right? But the problem with that is it's hard to do. We do, in general, need infinitely many of those terms to get the match that we're looking for. Because if we substitute a 0 in for t and look at y of x comma 0, we're going to get that same sum with that same coefficient a sub n, but with this building block function, sine of n pi over L times x, sum n equals 1 to infinity. And we need somehow for this to add up to my tent function shape in this example, say. Right? So the only way to make that happen is to choose these a sub n's, or calculate these a sub n's is maybe a better way to say it, choose so that they are the projection coefficients. This is where we left off in our story. The projection coefficients of our function f of x and 0. Actually, I should just call it f of x. I don't want to twist my notation here. F of x equals y of x and 0. We want to choose the a sub n's so that this series adds up exactly to the function f of x, the projection coefficients of f of x onto the direction of the function sine of n pi over L times x. And we discovered last time that to do that, to compute these projection coefficients, we need a new notion of a dot product that works for functions the way that the old dot product used to work for vectors. And so where we came out on the other end of that process was we decided that to project a function, let's call it f, onto another function, let's call it phi, that what we really wanted was phi, the function, times the ratio of two inner products, the inner product of phi with f and the inner product of phi with itself, where these angle brackets are used to represent the inner product, which is taking the place of what used to be a dot product of vectors. And last time we saw that this inner product was defined on two functions, by an integral. The integral from, I don't want to use a and b. No, maybe I'll use a and b. Is the integral in our example from 0 to L, because that's our domain of definition for all of our functions that are involved. The integral from 0 to L of the product of the two functions, a of x times b of x dx. And so ultimately what we'd like is to realize y of x and 0 as a sum of all of its projections onto these sines of n pi x over L. So we'd like this, sum of the projection of f onto sine of n pi x over L, and running from 1 to infinity. So when we finish today, what we would like is to have a formula that tells us the identity of these a sub n's. Okay? Tells us how to compute them. Because all we have to do is know how to compute them, and then they are going to piece together for us a solution for the whole initial and boundary value problem. Just having the cosine of n pi a over lt sine n pi over L times x, that's enough to satisfy the partial differential equation, the left-hand boundary condition, and the right-hand boundary condition. But we need to get the an's just so that they also satisfy the condition which is initial in time, the initial shape of the guitar string before we let it go. Right? So that's the formula that we need by the end of the hour.